So next, let's look at a slightly different situation. So we still have our two cart system here, cart 1, cart 2. Let's say cart 1 again is moving to the right with some velocity v1. Cart 2, let's keep cart 2 at rest. v2 equals 0 over here. But then let's say in this example that when the objects collide, instead of bouncing, as they did in our previous examples, they stick together. So after the collision, the objects are now conjoined. And as a result, they're going to move with a single velocity. Here, hang on just a second. Make that a little bit lower here. A single velocity that we'll call just v prime. It's no longer v1 or v2. It's just v prime, as we're looking at the velocity, combined velocity of the carts after the collision. So this situation, different from what we saw previously with elastic collisions, is called an inelastic collision. And in an inelastic collision, you're going to notice that the objects become entangled. That's going to be, in terms of observations, how we identify an inelastic collision. Objects become entangled. Momentum is still conserved, just like it was in the elastic collisions. But unlike the elastic collisions, kinetic energy would not be conserved in the case of an inelastic collision. When the objects become entangled, there's going to be energy lost as heat due to the interaction between the two carts. So kinetic energy would not be conserved in an inelastic collision. Again, we're not really focusing on energy, conservation of energy here in Chapter 8, so we're not going to talk much about that. But it is an important defining characteristic of an inelastic collision, that energy is not conserved. Some energy of the carts is going to be lost as heat here. And just like our previous examples, we are going to assume that this surface is frictionless, so there are no external forces acting on the two-cart system. There's an internal action-reaction pair, but because there are no external forces, momentum will be conserved in the collision. So what happens now mathematically is the equation's a little bit different. If we think about the total momentum before the collision, it's still m1 times v1 plus m2 times v2, like it was for our elastic collisions. But if we think about the momentum after the collision, we only have one momentum vector now because the two objects have become entangled. They effectively move as a single object with a combined mass m1 plus m2. And their momentum would be found by taking that combined mass m1 plus m2 and multiplying it by that velocity v prime, the velocity that the carts move with as a unit after they become entangled. So, using conservation of momentum, initial momentum, m1 v1 plus m2 v2, has to be equal to final momentum, m1 plus m2 quantity, m1 plus m2 times v prime. So we can write an equation then for conservation of momentum for an inelastic collision of m1 v1 plus m2 v2 equals the quantity m1 plus m2 times v prime. And that's it. That's our equation that we will use for conservation of momentum in inelastic collisions. So, assuming that these two carts have equal mass, in our example, v2 is 0, so m2 v2 would cancel to 0, which would make m1 v1 equal to m1 plus m2 quantity times v prime. And if the masses are the same, we could just call it m. So mv1 equals m plus m times v prime. And m plus m, we could just write that as 2m, right? So we could say m v1 equals 2m times v prime. And so we can find then that when we solve for v prime, it's going to be equal to m1 v1 divided by 2m. The m's cancel, so it's going to be v1 over 2. We're going to have half the speed because we've doubled the mass in the momentum expression. That's only going to work if the carts are of equal mass and the second cart is initially at rest. But that's one specific case that you might see. More generally, the equation will work even if the second cart has some initial velocity v2 and the carts are of unequal mass. We would just have to plug the numbers in and do the algebra to figure out what our final velocity would be equal to. So let's get the general expression back up there again. In cases where v2 is not equal to 0, we could still use this expression for an inelastic collision. Okay?